so if that's the case, I have this equation. Okay? So I would like to solve this equation for S bar. Okay? So I assume I know D, and I know mu m, and I know km, and I know ki. Okay? So this is the equation I'd like to solve. You could probably see that if you wanted to, you plug in the mu right there, you can multiply across, you can get a quadratic equation if you want to, right? So my goal is not to solve this with a quadratic equation, it's to show you how to solve it with this method right here. Okay? So here's the equation I want to solve. According to this method, what I do is I add x on each side of the equation. Okay? So that's what I've done here. I've added s bar to this side of the equation, which was 0, and then I added s bar to this side of the equation. Okay? And then I did what I did on the previous page. I took the unknown on the left-hand side of the equation and gave that index s plus 1. And then I gave all the s's on the right-hand side of the equation. I call those Sn. Okay? So that gives you an equation that looks like this. To use this, first of all, you have to guess the solution. Okay? You have to guess what s bar is. Okay, so just remember the index here means which iteration you're performing. So I'm going to guess what I think the steady state value of s is. And then I would put S0 into this equation there. Okay, I have all this other information. Then I would generate S1. Then I would take that S1 value, plug it in on the right-hand side, get S2, and so on. Okay, it's that simple. So it's very fun. Okay. So that's what's known as a fixed point. All right. So we talked about this method. I guess I'm going to go over the whole lecture again. It's just let's just go. All right. So method number 2. This is a better method, as I'll talk about in a moment. This is what's known as Newton-Raphson. So to start to derive the equation that we used to do this iteration, let's start with this. This is something you should remember. This is the first order Taylor series expansion of a function f. Right? This is first semester calculus. So you take your function f and you do the Taylor series expansion. You stop at the first order terms here. Right? There's other terms that involve like second derivative and x minus x r squared and so on and so forth. So this is an approximation. Okay. And then what we're going to do for this equation is we're going to convert this into an iterative equation as follows. Okay. So I'm going to take on the left-hand side of the equation, I'm going to substitute xn plus 1 for xn. And then on the right-hand side of the equation, I'm going to, well, let's just put it this way. I'll be clear. Every time I see x, I'm going to substitute x plus 1. And every time I see x bar, I'm going to substitute xn. Okay. So remember, when you do these expansions, you have to do them about some point, right? So this is an expansion about the point x bar. So every time I see x, I'm going to substitute xn plus 1. And every time I see x bar, I'm going to substitute xn. Okay. Then I get this equation. Okay. And my goal here is to find xn plus 1. I want to generate an iterative equation that, given xn, I can compute xn plus 1 for my next iteration. So I'm just going to take this equation here, and I'm going to solve it for xn. It looks like this. Okay? If I just take this equation right here, solve it for xn plus 1, you get this equation. Okay. So what is this? How do we do this then? So to evaluate the right-hand side of this equation, you need to know the function f, obviously. You also need to know the derivative of the function f. Okay? So I need f, I also need its derivative. And so to evaluate this, for example, if I have a guess x0, then I evaluate the function at x0, I got the derivative at x0, and then I put x0 there, and then I compute x1. Okay? And then with x1, plug it back in here, and generate x2, and so on and so forth. Okay? So at this point, it's not clear why you would do this versus this, which I'll explain in a minute. Okay? All right, so this is how it works. You have to give me the function f. You have to give me the derivative of the function f. You have to give me an initial guess. Okay? And then I'm going to compute this thing, and eventually I have to stop. You can't go on forever, right? You guys have never programmed, but there's something in programming called an infinite loop where you go around the loop forever. Your computer would just freeze. we scale by this number. That's what kind of defines what we mean by close. Okay? So this is what you would get if MATLAB does something like this. This thing here is called tolerance. Okay. So that's something you specify when you solve a problem. For example, in MATLAB, MATLAB has default values it uses. Okay. And so if MATLAB got this, reached this condition, it would say, it would come back and say, I've satisfied the tolerances. That means it worked. Okay. It got really, really close to the answer, and then it stopped. This thing is often like 10 to the minus 6 or something like that. It's like small. Okay. So it's really getting close. Okay. The other option is this one here. Okay. MATLAB will say, I've reached the maximum number of iterations. Okay. So this is often a number like 500 or 200. So in other words, it's gone through this iteration 500 times, and this condition was never satisfied, and then it just stops. You see, because the code you can get in a situation in many cases where this will never be satisfied. Okay. Maybe because you made a bad guess, for example. And so it has to stop sometime. So it'll just stop after 500 iterations. And if it stops because of this, that means it failed. It failed to reach a solution. Okay. So as we learn to use MATLAB, you've got to interpret the messages that come back. If it comes back and says tolerance is satisfied, that's something like this. That means it worked. If it says maximum iterations reached, that means it didn't work. Okay. All right. So let's see what I'd like to cover on this slide. All right. So this says basically, when does this method work? So at this point, we have method 1, right? And I kind of told you when this was went over last time. And then we have method 2. Okay. The reason we like method 1 over method 2 is because this one tends to converge much faster. Okay. So what's the disadvantage of this method is you need to know the derivative, right? You don't need to know the derivative of the function in this method. The advantage of the Newton method is that it tends to converge much faster. It might converge in 5 iterations. The fixed point might take 50 iterations or something like that. If you have a single equation, it doesn't make any difference because it'll happen so fast you don't know what happens. But if you're solving a very big problem, like 100,000 equations, then the number of iterations really matters. Okay. So that's why we care about this. So this just gives the conditions under which this method works. Okay. So let's just go over this real quick. It says, first of all, the function has to be 3 times differentiable. In other words, you have to be able to find the first 3 derivatives of the function have to be defined. Okay, that's not very restrictive. Second order derivative has to be non-zero at the solution. Okay. So that's probably going to be okay. You could get a pathological case where the second derivative of the function is actually 0 at the solution, but probably not too likely. Okay. X has to be sufficiently close to S. Now that should raise a red flag to you. Like, I don't know S. If I knew S, I wouldn't do this. So how do I ensure that my guess is close? The answer is you cannot. Okay. So this is something you see a lot with nonlinear systems. This is what's known as local, right? So it basically says if you guess close to S, this is going to work. If you guess too far away from S, it won't work. Okay. And there's no easy way to define what close means. That's obviously one problem here is this. If this derivative becomes 0, we're screwed. That's a technical term. Okay. Right? If this derivative becomes 0 at any value xn, then this thing's going to blow up. Okay. That's called a singularity. All right. All right. So this is really interesting. I'm going to give you an example. This I gave you in the set of notes. I think. Remember, I posted a set of PowerPoint slides with all the examples. This is one of the. Everyone is like, thank God. Right? This is one of the examples in the notes. So rather than write it down, let me explain what I'm doing here. Right? So this, what am I trying to do? I'm trying to solve this problem again. Okay. Right? I'm trying to solve this problem for steady state values of x. So this is the Newton method here. And all I've done is rewritten this method saying my x in this problem is called s. S bar, actually. Okay? So to be able to do this, I have to take the derivative of my function that I'm trying to solve. Sorry, I need to evaluate my function at some value, and also have to evaluate the derivative. So I need to know the function evaluated here, and I also need to know the derivative evaluated here. Okay? So that's the function. If you go back, right? Am I going the wrong way? Yeah. Okay, there's my function there. So that's my f of x, or f of x, s bar. And so all I'm doing here is evaluating that at Sn. It's not rocket science, people. All I do is just take the function u, and every time I see s, I put in Sn bar. Okay? So that's how you evaluate the function. To evaluate the derivative of the function, first of all, you have to know the derivative. Right? So if I take the derivative, right here. If you take the derivative of this function here with respect to s, d doesn't depend on s. That's the same as the derivative of mu. Okay? And I've used the quotient rule to do that, right? The problem here is mu looks like this. And s appears the numerator and denominator, so you have to use the quotient rule. Okay? You get something nasty looking like this, and every time I saw s bar, I just plugged in Sn bar. Okay? So in other words, to apply this method, you guess in S0. You evaluate this thing in S0, and then this thing in S0, then you get this, S0 here, you generate an S1. And then you do the same thing again over and over again. Okay? So the main thing is you have to evaluate not only the function, but you also have to evaluate the derivative of the function. All right? You need to memorize this equation. All right, let's go. Secant method. So the idea here is that we like this method here. We like it because it converges quickly and it converges under violent assumptions. But we don't like the fact that it involves a derivative because derivatives are expensive to compute. And therefore, we like a method that's similar to this but doesn't use the derivative. Okay? So the way to do that is something called the secant method. And so all we do here, okay, is to, instead of using the derivative, we use an approximation of the derivative. Hopefully you agree with me that this looks like an approximation of the derivative. Remember the definition of the derivative? It's something like this, and the limit is these two values go to 0, delta x. Okay? So, what we're doing here is we're saying we want to approximate the derivative. We're going to approximate that as the value of the function at our current value minus the function at the previous value divided by the difference between the two values. This looks like delta f over delta x. Okay? If these two are really close to each other, then that's a good approximation of the derivative, otherwise maybe not. Okay? But we'll use it anyway. And so now that we have that approximation for the derivative, then we can go back to the Newton method here, which is this method right here. And we can take that approximation and use it, plug it in right there, okay, instead of the derivative. And if you do that, you get this, right? So this was the iteration. Xn plus 1 equals xn minus the function evaluated xn, and then this was divided by the derivative. So in other words, 1 over this thing right there. Okay? So same kind of game here, right? In order to evaluate this function, well, this looks a little bit different. All right, so to get this iteration started, you want to generate an x1, right? You need an x0, no surprise there. You also need an x minus 1, right? That could be an issue. Where are you going to get x minus 1? You agree with this, right? like you guess it doesn't work. If you know nothing about the method, you would just come back and tell me it didn't work. And then I would ask you to try another guess. You'd be like, why would I do that? And I'd say, well, convergence depends on the guess. Okay. So, in other words, we're going over the methods so that you have enough background that when you use these tools, you have some ability to know how to use them and you interpret whether they're working or not. Okay. All right. So with that out of the way, so we want to be able to solve these in MATLAB. Okay. There's two functions available in MATLAB to do this. One is called F0, in other words, find the zero of a function, and another one's called fsolve. Okay. So this F0 solves a single equation and a single unknown. Okay. One function, one unknown. Like the problem I just gave you with the bioreactor. Okay. So I must have stole this from the website. Right? Finds the root of the continuous function of one variable. Okay. So this is how it's used. Okay. And this is the way all MATLAB things are used. So you have to kind of get familiar with this. Okay. So there's a function called F0. That's supplied by MATLAB. You just use it. Okay? These are arguments of the function. That means in order for MATLAB to solve the problem, you have to provide the things in the parentheses here. Okay? The first thing you have to provide is the initial guess. It's called X0 here. Okay? You have to guess what you think the answer is. I'll give you some examples of this in a minute. The second thing you have to do is have fun. Now, you have to provide a function that evaluates this, right? So hopefully this makes sense to you. You have a program here that solves nonlinear algebraic equations. It has to know what equation you want to solve. Like, how's it going to know otherwise? Okay. That equation that you want to solve is called, in this case, function. Okay. It's put in parentheses, and you have to write this function. You have to write a little equation for this in MATLAB. I'll show you how to do it in a minute. Okay. So you have to guess the answer, and you have to provide a function to solve it. Okay. And then what it does in principle is it runs and it gives you the answer back as x. Okay. There's nothing magical about this names. This is what's known as the syntax has to be this, but I could call the initial guess anything I want, I call the function anything I want, and I call the answer anything I want. But generically it looks like this. Okay? All right, so if you look at what the algorithm uses, it uses a combination of three things, only one of which you've heard: bisection, secant, and inverse quadratic interpolation. Feel like I've never heard of that. Okay, that's all right. Okay, they're just more advanced methods. That's what I mean. So you would write a code that would use like fixed point iteration. The methods they use are much more advanced. Okay, they're more advanced meaning what? It means they converge faster and they converge more reliably than the methods you would probably come up with. But the same thing